So, continuing our discussion about myoglobin and hemoglobin and structural implications for how they both bind and interact with molecules like oxygen. So we're starting to look at myoglobin and seeing what it's capable of. So the question here is, can myoglobin transport oxygen? I'll say that this is a bit of a trick question. Of course it can. It absolutely can carry oxygen from point A to point B. And point A might be in your lungs, where the oxygen is taken out of the air and moved through the lungs into your bloodstream. And you would oxygenate myoglobin, and then it would be off through your arteries to tissues that need oxygen. So yes, myoglobin absolutely can transport oxygen. The problem is that it binds oxygen too tightly, and it won't drop it off once it gets to point B. Right? So if your heart needs oxygen, myoglobin is a poor choice because, sure, it can carry oxygen, but it's not going to drop it off where you need it. And this is kind of apparent if you look at the binding curve for myoglobin. All right, so on the on the right side of the screen, we have our percent occupancy on the y-axis again. We have our concentration on the x-axis, and this is concentration of oxygen. The fact that it's expressed as PO2 means partial pressure of oxygen. Oxygen is a gas, so we talk about it in pressures, but it's absolutely equivalent to concentration, so there's not much to worry about here. So what we can see here is that the KD, right, the concentration required to fill 50% of the sites, is very, very tiny. It's way less than 1 kilopascal, right? So these units are in kilopascals. 1 kilopascal is probably around here somewhere where my mouse is, and we are way less than that. So we're maybe at 0.25 kilopascals. So, like I said, myoglobin is a very tight binder of oxygen, and because of that, it's easily saturated, and it also means that it's not easy to get the oxygen out of myoglobin once it gets in there. So, like I said, trick question. It absolutely can transport myoglobin. It just isn't going to do a very good job because it won't drop it off when you need it. Okay, so, right, myoglobin is not a good answer to our problem here. Let's see if we can figure out something that is. Well, let me go back a second here. And I want to talk about, real quickly, arterial blood versus venous blood. So if you look at arterial blood, I know we're talking about myoglobin here and blood has hemoglobin, but if you talk about arterial blood, you're typically talking about something like 96% oxygen saturation. If you're talking about venous blood, you're talking about something like 64% saturation. So roughly 30% of the oxygen that's carried by hemoglobin gets dumped when it gets to the right place. So when it gets to tissues that need oxygen, it easily gives it up. And remember at the very beginning, we said that it's hard to take gaseous oxygen and dissolve it in water. It does not like to be there. So just to give you an idea, with hemoglobin, we can actually make 100 milliliters of blood carry about 6.5 milliliters of oxygen gas. I know that doesn't sound like a lot, but when you consider or compare that with the amount of oxygen that you can dissolve in water, it's actually quite a lot. Okay, so, all right? We have this problem. This first curve, the one that saturates the quickest, that is for myoglobin. And if you think about this, right, we said that it's not a good option for transporting oxygen because it won't release it when it gets to the place it needs to go. And by looking at the graph, that's pretty easy to see. So if we look way over here at about 13 kilopascals, we can see that myoglobin would be nearly 100% saturated. Now, if we drop down in pressure to about 4 kilopascals, which is roughly the pressure of oxygen in tissue, we still see that myoglobin is 100% saturated. So like I said, myoglobin is terrible because it won't give up the oxygen once it has it. We could go with a lower affinity binder. So, right, this low or this bottom curve here represents a state of hemoglobin where it binds easily and releases easily. And same game, right? If we go up to about 13 kilopascals, we see that our concentration of, or our occupancy is about 50%, our saturation is about 50%. And then if we go down to 4, we can see that we're at about 25%. So it works. We have the ability to pick up some oxygen when we're in the lungs, but not a lot. And when we get down to the tissues, we can drop off some, but again, not a lot. So it would be nice if we could have this hybrid curve, some way to take the best of both worlds, right? The high affinity or high saturation when we have high pressure in the lungs, and then the ability to dump a lot of it when we get into low pressure areas like tissue. So we want to talk about how this happens. So there are a few things that we need to do to make this happen. One thing is that we want a protein that has multiple binding sites. So the way that we're going to do this is not with myoglobin, but with hemoglobin. So hemoglobin is comprised of 4 subunits, 2 alphas and 2 betas. The alpha subunits are about 141 amino acids. The beta subunits are 146 amino acids. And the alpha and beta subunits are about 50% identical. So if you were to take the amino acid sequences of alpha and beta and compare them, you would find that roughly half of the amino acids in those 2 chains are the same. The other half is different. So again, if you're still thinking back to the central dogma, that might be a little bit problematic for you because you know that sequence, DNA gives you sequence, protein sequence. Protein sequence gives you structure, and structure gives you function. And I'm telling you that alpha chain and beta chain in hemoglobin are 50% identical, only 50%, yet they have the same job and the same structure. So they have the same function. So as a very rough rule of thumb, biochemists and structural biologists and people like that, we typically say that any sequence identity greater than 30% gives you roughly the same protein structure and gives you roughly the same protein function. So we are above that. We're at 50%. the alpha and beta chains therefore have the same structure or very close, and the structure of the individual monomers is very, very similar to myoglobin. Okay, so, right, we said that we can get this hybrid middle transition from low to high affinity state, right? We want this middle curve. And the way that we're going to do that is creating a protein with multiple binding sites. And these binding sites have to be able to talk to each other. And I don't mean that binding site 1 is going to be like, hey, Bob, how you doing? How's the day? How are the kids? No. I'm saying that when oxygen binds to binding site 1, it induces small structural changes in the surrounding protein structure, and those small structural changes get transmitted to the neighboring proteins, right? So in hemoglobin, you have an alpha and a beta subunit sitting next to each other. So if oxygen binds in the alpha subunit, you get structural changes in that protein, and those structural changes get transmitted to the beta subunit, which undergoes its own set of structural changes, and that opens up the binding site so that oxygen binds easier.